Spring 1983. I am having lunch with a graduate student named Danny Hillis. He is from the MIT Artificial Intelligence Lab. Smart kid. Eager. And he tells me he is starting a company. A computer company. But not just any computer. He wants to build a machine with 1 million processors, all working at the same time, in parallel. 1 million. The first real machine would have around 64,000. Far smaller, but still insane by any standard. I looked at him and said, "That is positively the dopiest idea I ever heard." And by the end of that lunch, I had agreed to join him. Let me tell you how a dopey idea turned into something that actually worked, and why I couldn't resist being part of it. You have to understand something about me. I've always loved computing, not the theory, not the conferences, the actual work. Back at Los Alamos during the war, we didn't have electronic computers. We had people, rows of people, sitting at desks with mechanical calculators, passing numbers back and forth on index cards. I organized them. I figured out how to make them work faster, in parallel, each person doing one piece of the problem while the next person waited for their input. That was my first parallel computer, made of humans. We calculated bomb yields that way. Differential equations were broken into pieces, each piece handed to a different person. When one person finished their part, they passed the card to the next. Assembly line mathematics. It worked. It worked beautifully. And I never forgot how powerful it was to have many minds working on one problem simultaneously. So when this kid, Danny Hillis, told me he wanted to build a machine that worked the same way, 1 million little processors all talking to each other, all working on pieces of a problem at the same time, I thought it was crazy. But I also thought, what if it isn't? That's the thing about crazy ideas. You can't know if they're crazy until you try to prove them wrong. And proving things wrong is what I do for a living. So I said, yes. I told him I'd spend the summer in Cambridge, near Boston, working at a startup. I was in my mid-60s. Most people my age were retiring, giving lectures, accepting honorary degrees. And here I was, signing up to work at a company that did not even have a working product yet. Most people thought I was nuts. Maybe I was. What I did not expect was what I found when I got there. The company was called Thinking Machines. It was the very beginning, the kind of place where the vision existed before the machine did. They had money, investors who believed in the vision. They had a beautiful old building in Cambridge, like some kind of mansion converted into an office, and they had absolutely nothing built. Papers, stock certificates, whiteboards covered in diagrams, but no machine, no working prototype, just ideas and enthusiasm. They offered to make me an advisor, a consultant, someone who shows up to meetings, nods wisely, and collects a check. I told them that sounded like a bunch of baloney. Give me something real to do. They looked at each other. Then someone said, "Well, there is the router. If you are finding this story valuable, consider subscribing. I tell stories about the moments that shape the greatest minds in physics, the moments they do not teach you in textbooks." The router. That was the monster at the heart of their crazy machine. Here's the problem. You want 1 million processors to work together, but 1 million processors means they need to talk to each other, send data back and forth, and you cannot just connect every processor to every other processor. That would be 1 trillion wires. Impossible. So you need a router, a traffic system, something that takes a message from processor A and figures out how to get it to processor Z without everything crashing into everything else. The engineers had been working on this for months. They had theories, they had simulations, they had arguments. What they did not have was an answer, so I sat down and started thinking about it my own way. Now here is the thing. I am a physicist. I think in continuous quantities, differential equations, flows and rates. The engineers were thinking in discrete steps. This gate, then that gate, then this buffer. I decided to analyze their Boolean circuits as if they were a continuous differentiable system. Treat them with partial differential equations instead of discrete logic. See what the math told me. My equations said they needed 5 buffers per chip. Their discrete analysis said 7 per chip. 7 buffers meant bigger chips, more cost, more heat, and a machine that might never ship. They ignored me at first. They thought I was doing some kind of physics trick that did not apply to real circuits. But when the chip design turned out to be too big to manufacture, they had no choice. They went back to 5 buffers, and the router worked. I did not say I told you so. I did smile. One of the young engineers came up to me afterward and asked how I knew. How could differential equations, tools from physics, tell you something about digital circuits? I told him the universe does not care what field you think you are in. The math is the math. If the equations work, they work. Do not let disciplinary boundaries stop you from using the best tool for the job. That is the thing about approaching problems from a different angle. Sometimes the wrong way of thinking turns out to be exactly right. And when the machine finally ran its first program in April 1985, with Conway's Game of Life flickering across those processors, I felt something I had not felt in years. The thrill of watching a crazy idea become real. But the router was not even the biggest contribution I made that summer. The real surprise came when I started asking a simple question. What is this machine actually good for? Everyone at Thinking Machines assumed it would be used for artificial intelligence. That was the fashion. Neural networks, pattern recognition, machine learning, all the buzzwords. They thought 1 million processors would finally crack the AI problem. I was not so sure. So I decided to test something else. What if you use this machine for regular scientific computing, number crunching, the kind of calculations physicists do every day? I picked quantum chromodynamics, QCD, as my test case. It is the physics of quarks and gluons. It is one of the hardest computational problems in physics. Nobody thought that would work. The whole architecture was designed for artificial intelligence. Using it for QCD seemed like using a sports car to haul lumber. But I wanted to know for sure. And when I want to know something, I do not ask. I calculate. I wrote a little program in my head, a parallel version of BASIC, the simple programming language. I worked out how you could split a physics calculation across thousands of processors, each one doing a tiny piece. Then I simulated it by hand with pencil and paper. I walked through the logic step by step, pretending I was the machine, figuring out how fast it would run. This is what I mean by real work. Not reading reports, not sitting in meetings, actually doing the calculation yourself, so you understand it in your bones. And when I finished, I went to Danny and said, "Hey Danny, that machine of yours can actually do something useful." He was surprised. The AI team was surprised. But my calculation showed that their architecture could be genuinely competitive for serious numerical simulation. It would be fast enough to matter for real scientific work. That insight pulled the company towards serious scientific work. Thinking Machines went from being seen as an AI toy to being a real platform for numerical simulation. Real physicists started using it for real research, and it all came from asking a simple question and doing the work to answer it. There's one more thing I'm proud of from that summer. Danny asked me to work on a specific problem. How do you calculate logarithms on a massively parallel machine? It sounds technical, but logarithms are everywhere in scientific computing. If you can calculate them fast, everything runs faster. I had actually thought about this problem before. Back at Los Alamos, when we were doing bomb calculations with our human computers, I had figured out tricks for computing logarithms quickly. Mental shortcuts. Ways to break the problem into pieces. Now I adapted those tricks for Danny's machine. I wrote a subroutine, a little piece of code, that could calculate logarithms faster than anything else they had. It wasn't glamorous. Nobody was going to write newspaper articles about a logarithm subroutine, but it was real. It was useful, and it made the machine measurably better. That's what I cared about. Not credit, not titles. Just, does it work? Is it real? Did I actually contribute something? The answer was yes. Looking back, I think that's why I joined thinking machines in the first place. I was in my mid-60s. I had won the Nobel Prize. I had nothing to prove to anyone. I could have spent my summers on beaches or at conferences, being treated like a distinguished elder statesman of physics. Instead, I went to a startup in Cambridge and worked on a crazy computer project with kids half my age. I helped wire the computer room, set up the shop, install the phones, whatever moved the project forward. I sat on the floor and argued about buffers. Why? Because that's what being a scientist means to me. You don't understand something until you've done it with your own hands. You don't know if an idea is crazy until you've tried to prove it wrong. And you never, ever let someone turn you into an advisor who just nods and collects a check. Danny Hillis later said that I was unlike any consultant he'd ever had, that I refused to be treated like a visiting dignitary, that I wanted to be in the trenches, doing the work, making mistakes, figuring things out. He was right. That's exactly what I wanted. The connection machine, that's what they eventually called it, went on to become one of the most important supercomputers of the 1980s. It was beautiful too. A big black cube with blinking red lights, like something out of science fiction. Scientists used it to simulate everything from fluid dynamics to quantum chromodynamics. It proved that parallel computing was not a dopey idea after all. And I was there at the beginning, not as a name on a letterhead, not as a wise advisor giving speeches, but as a guy with a pencil, working out whether 5 buffers or 7 buffers was the right answer. That's the kind of scientist I always wanted to be. That's the kind of scientist I was. I was Richard Feynman. I won the Nobel Prize for quantum electrodynamics. I helped build the atomic bomb. I taught a generation of physicists how to think. And in the summer of 1983, I joined a startup because a kid told me the dopiest idea I had ever heard. And I wanted to find out if he was right. He was. If this story resonated with you, subscribe and join me for the next one.